changed.
You're recording.
Yeah, I had a chat. I think Leafy's happy to just record it, and then the things that people want to watch back, we can. If it's if Leafy doesn't want to keep the recording, we'll remove it.
Okay, I'm just going to put this in presenter view and then see if you guys can still see it. Can you guys still see the main screen?
Yeah.
Yeah. Cool. Okay, so I put together this presentation. It was mainly for myself because I was at a point in my thesis writing where I needed to interpret all my DLS data and collate all that together. And throughout my PhD, I've learned bits of DLS, but I forget things very easily. So I kind of just went back to basics and went through it all in my head and figured as I made these notes, I could share it with people. But just an FYI, it's a bit kind of, I've not really practiced or prepared for this presentation as such. It's just talking through these kind of notes and understanding that I had. So hopefully it's enough just to like have a discussion, but I didn't want to spend too much time on it because I need to get going with thesis writing as well. So yeah, please feel free to like chip in if you think, oh, actually I understood that a bit differently, or yeah, just jump in whenever basically. Just actually, first of all, out of curiosity, who either uses or needs to use in their projects DLS? Just so I know. Sorry, say your name because I can't see it.
I use it.
Cool, Sarah. I know Alethia does.
Yeah, as a group we do, so I haven't specifically yet. But
yeah, cool. Cool. Okay, so hopefully this doesn't like apply to nearly everybody. Cool. Okay, so yeah, as I say, jump in wherever. We all do DLS to ultimately try and understand the size of our particles. I'm not sure anyone at the moment is using it for, or sorry, how many people use it for the oh my goodness, mind blank. For measuring the charge on it, or most people just use it for size.
Just the size for me.
Size, yeah.
Size mainly, but both.
Both, yeah. Okay. Cool. Okay, yeah. So this presentation is mainly just going to focus on the size because I haven't yet had to use it for charge. So yeah. So ultimately, the technique of DLS is going to determine the hydrodynamic size of particles, and it bases on the Stokes-Einstein equation, and it does this by calculating the diffusion speed through analysing the time dependence, which is something they in which you use an autocorrelation for the intensity of scattered light. I'm basically going to work through the background to each of those things and go through how yeah, data interpretation. Okay, so back to like real basics. Essentially got a sample of particles, and the principle is that we're going to shine a light or a laser onto that particle and see how that light is scattered. So if you had a camera or a screen where you could see the scattered light pattern, you would see this speckled pattern, and you'd have black spots where the phases of light have gone and hit your detector and cancelled one another out, or you would have an additive effect from light that's in phase and building up one another, creating light spots. And then the spectrum, or kind of white to black, can be measured as intensity. And essentially what the detector is going to be looking at is how over time those speckle patterns will be changing, and how quickly that changes is due to Brownian motion, so the random movement of particles in a solution. So for large particles, you would expect them to move quite slowly and have I don't know if you can see my cursor when I move. Can everyone see that? moving? No?
Yeah.
Cool, thanks. So yeah, you would, for a slow moving particle, you would expect intensity over time to have a profile like this, or for small particles which will move much quicker due to Brownian motion, you would see a pattern like this. And essentially it's this speed of diffusion that the DLS is going to try and measure. And so the DLS itself has a bit more of a complicated setup, but essentially you have your laser, which then passes through something called an attenuator, which will control the how much light is passed through, and which then hits your sample, and you have detectors at different positions. So if anyone used to use the DLS over at Highfield, ours was the nano, I think it was the ZS, S or ZS. So it had a detector at 173 degrees, whereas the one that we've now got in IDS is within the Z Ultra and has a third detector, but that will be relevant a bit later. I'm just going to talk through like the real basics for now, and then if we have time we can discuss how the new one like differs. So basically the detector is just going to be counting photons of light over a set of time, and then that signal gets processed through a process using an autocorrelator, which we'll go on to talk about. But essentially the detector is just counting photons, which is your intensity over time. So what the processor does, because ultimately to understand the size, it uses a technique of understanding how quickly your intensity profile is changing. So it's not detecting specific changes in the intensity, but rather how your intensity signal is, how quickly it changes with time, if that makes sense. So it's a time dependence of your signal, and it can do that by doing an autocorrelation. So I'm going to try my best to talk through what this essentially means. So to find out how quickly your intensity profile is changing, what an autocorrelation does is just pick a time, a set delay time, which here is referred to as tau, and then it reads off, it will move your signal along and read off the intensity and plug it into this rather complicated equation down here. But essentially what we're interested in is once we put in inputs of our delay time and intensity, we get a readout called your correlation coefficient, which can be plotted against the amount of time in which you choose to delay. So essentially the computer does this really quickly, but once it inputs a delay time, it will shift that signal, and then it will read off the intensity and plot it against that delay time, and then by that delay time again, so now we've got 2 tau, it will plot your output correlation coefficient against your 2 tau delay time. Does that so far make sense to everybody? Yay? Hey?
Yeah.
Yeah, cool. Okay. Yeah, jump in if it doesn't make sense. So what's this essentially doing is telling you, if you say, for example, your signal was, your intensity was going quite slowly when you have large particles, if your intensity is staying the same for quite a long amount of time, this is going to depict that. And so you have your autocorrelation for small particles moving quite quickly would look something like this, whereas if it was a large particle, it's going to take longer for this a copy of the signal itself to change, and therefore look more like this. So in essence, an autocorrelation is a way of auto, because your signal is laid over itself, it's correlating to itself, autocorrelation. And then basically it gets processed by changing that into a log expression. So this this then is your raw data that the DLS will show. So your correlation coefficient and time on a log scale. So this is actually something I never actually realised at the start of my PhD, that, yeah, the raw data, if you're ever going to look at that from a DLS, this is what you want to be looking at. And it gives you a lot of information about your sample straight off.
Yeah.
So, sorry.
So I think that, Leafy, I think that you explained that really well. I followed that. I guess if you, just with regards to that curve you're showing there, if you had, let's say, some really small particles mixed in with some big lumpy ones, I'm just wondering what this curve would look. Would it look like a kind of double hump, like a sort of
Yes.
you know, like in a melt curve when you've got two peaks?
Yeah.
That's kind of what I'd say. It's sort of, yeah. So there's two components almost. Yeah. A big one and a little one, and then you see it as a change in the shape. Great. Yeah.
Yeah.
I'll follow that.
Look like, yeah. Yeah, which I'll get onto actually as well, Nick. That will come up. Yeah, sorry. So a few things you can actually like straight away take from if you're looking at this raw data. The first of which is where your sample, where on your y-axis the signal intercepts is a readout of how much signal to noise ratio you've got. So noise obviously coming from the system itself, which is worth saying that 1 is not possible. I'm just going to jump back a little bit. So this at the bottom of this equation, you've got a function that will essentially make sure that at time 0, your correlation coefficient is equal to 1 rather than 0. But because your system is always going to have some noise, it can never be perfect and it won't ever be 1. But it's generally accepted that if you have an intercept between 0.8 and 1, that's a good sample. You then also can look at when your exponential decay begins, and if it's a small particle, and so it's going to be changing, the signal upon itself will be changing quickly, you expect it to start at an earlier time, whereas a large particle, you would expect this exponential to start much later. So it can tell you a bit straight away about the size. The gradient of this will tell you about the polydispersity, which essentially is for those whether you've got a mix of particle sizes or your particles are all exactly the same size. So particles all exactly the same size are known as monodisperse, multiple sizes polydisperse. And so the more steeper this gradient is, the more monodisperse of the same size your particles are. And then finally your baseline, if you were to have a lot of kind of static or fluctuations down here, that suggests that you are getting some interruption from aggregates or dust particles. So they're just 3 things you can look at straight away on the raw data to assess whether you've got a good sample you're measuring or not.
It does remind me a bit, Leafy, of melt curves in PCR. You know, if you've got one single transcript length, you get a very steep, because you've just got one event basically, so one size at which it separates, so you get a very steep curve. If you've got a wide range of transcripts that increase, let's say, in one base pair within a sample, that's exactly what you'd see. You'd see a much shallower curve, and if you had 2, one short and one long, you would see a double hit. So it feels to me quite, I'm understanding this in the same way that I understand the melt curve in PC. I don't know, probably other people have not looked in so much detail at PCR melt curves, but it's anything where you've got a rate of change of something. That's kind of what you're measuring here. It's the, and I guess if you looked at the curves, like if you've got lots of tiny small stuff, it would be a jiggly line like that. And if you've got lots of small stuff and then some lumpy stuff, it would be the jiggly line but going up and down like that. So you'd have the jiggly stuff superimposed on the lumpy stuff.
Yeah, it's definitely, it looks like qPCR people are familiar with that as well. Okay, so within the DLS, it then so the raw data it pumps out after an autocorrelation function is this what's called correlogram. The but then the DLS has some algorithms which it applies to then analyze this raw data to understand what the size is. And it does two types of analysis. The first one is cumulance analysis, and the second one is a distribution analysis. So I'll go on to just try my best to explain those. Okay, so
Leafy, can I just ask again?
Yeah.
I'm sorry to bore on this. So I guess that graph on the right hand side is essentially the differential of the middle one. So it's the rate of change. Again, like the melt curve peak, it's it changes a lot and then it's steady for a little bit at the inflection part of the curve, and then it changes rapidly again, and then there's no change. So I wonder whether that's what it is.
Or sorry, this end graph.
Yeah, that end graph is the differential of that first graph. So when the curve is absolutely flat, there's no change at all, so you get 0. When it starts to change, then you get this rapid, and where the rate of change is the highest, is the peak. That's where the curve is the steepest. Then as the curve starts to flatten out again, that rate of change decreases until again it's flat, where your middle curve is horizontal.
I'm aware that particularly for the distribution analysis, it does some complicated maths to get that, but the two are definitely, you can see it as a differential, although I don't think that's the maths it applies to it.
I think I'm oversimplifying it a lot.
But
I think
it's related.
If you had a physicist or a mathematician look at that, then they'd be saying, like, what about the units? Because if you differentiate or integrate those, you do not get time from size. So there's some issues there, but I like the way you're thinking about it. It makes sense.
Okay, so some bits you kind of need to understand is that correlation coefficient, this GT, can also be or essentially, sorry, this parallelogram that we see here, which is a plot of your GT over time, can be expressed as this equation at the top here. And within this equation, you can solve for D, your diffusion coefficient. And this then is the value that gets plugged into your Stokes-Einstein equation down here, which can give you the hydrodynamic diameter. So essentially, the algorithm maths is going to be doing that. So it applies this equation, finds D, which then, if you put into this equation, can give you your hydrodynamic diameter. And it's worth noting that within these equations, you're seeing all the factors that kind of need to be controlled. So particularly in this Q value here, you've got your refractive index of your dispersant. So that's why you always need to be using the same dispersant with samples. So we use PBS. What needs to be known is your laser wavelength, your scattering angle, as well as controlling for temperature over here. So these values obviously are all plugged in when we set up the machine. So we set it to be a constant temperature. We tell it what type of dispersant with what refractive index we expect from it, yada, yada. So that's essentially the principles behind cumulance analysis, and what some very clever complicated maths does that I don't really understand. But essentially what it does is fit one exponential curve to your parallelogram, and it's the one that best matches. So for example, this is really like, the data is not representative, but it's just to illustrate, your cumulance analysis would find this red line here probably fits your parallelogram the best, and then it would plug that into this equation and find your D average, put that into your Stokes-Einstein equation, and that is what's referred to as your Z average. So what's important is it assumes only a single a single fit, basically, only one curve. And so your Z average that you have out very specifically is an intensity weighted mean diameter derived from cumulance analysis. So yeah, that's what Z average is. Any questions on that? No? Cool, okay.
Sorry, Leaf, I was just saying, but so basically you fit the curve to a single exponential model, and then you see how well that fits the curve by looking at r squared or chi-squared or something like that.
Whatever. Yeah.
I guess you can fit it to 2 exponentials as well, for like 2 populations.
Although for cumulance analysis, it only tries to fit 1. It won't try and fit 2. It just tries to fit 1.
Sure.
Yeah. And so that's where you get your Z average. So as Nick mentioned earlier, what's important to know is that if you did have a sample where you have 2 sizes, and so you have this 2-humped parallelogram, sorry, I can't say it very well, and it tries to fit one exponential, you're obviously going to it's not going to it's not going to represent the samples that are there. It won't match. And so this is where you need your distribution analysis instead. So it's just worth noting that if you ever have 2 peaks, or if your parallelogram ever has 2 humps, your Z average is not going to be a reliable readout for the size of your sample. You have to look at your distribution analysis instead. And so the other value that your cumulance analysis is going to pump out is your polydispersity index, which is just, again, some clever maths that's put on a scale from 0 to 1, which will tell you how uniform your particles are, whether they're, as I said earlier, monodispersed, they're all the same size, or polydispersed, they're of multiple sizes. And what you're looking for is something that's less than 1. Yeah, and so it's just how much your samples are distributed, and it works it out for a hypothetical Gaussian distribution. So just bear that in mind as well. It is just a kind of an I say arbitrary, but it's a value they work out assuming a Gaussian distribution, and it gives you that number from 0 to 1. So when you old style DLS, you would be given this, and so your cumulance analysis results, all you're looking at is these 2 numbers here. And so then on to the second bit of analysis it does, which is a distribution analysis. And rather than fitting 1 curve, it fits multiple exponentials. So it essentially it will try lots of those exponential fits and see how much it matches. And it does this using some clever maths. If you want to ever look it up, it's called non-negative least squares, or contin, but there's no need to get into what they do. But essentially it's going to it creates a histogram of sizes. So it will try lots of different exponentials that would be equivalent to different size particles, and then when it fits, it kind of plots the intensity, the highest at the one which is the best fit, if that makes sense. This then essentially just gets you, rather than seeing in a histogram viewpoint, you just see it as this peak size versus intensity percentage. Any questions on that? No? Cool.
No, it's really clear.
So yeah, of your results, then from your distribution analysis, it will plot this histogram, and then from this you can also then look at the peak size here. And if you had multiple peaks, you would then be looking at, it plugs out the size for each of those peaks. And so if you had a sample that was completely monodispersed, you had a PDI of 0, your Z average and your peak here would match perfectly, and you would just see a straight line, basically. Obviously that never happens. So what's also worth noting is this intensity plot is always biased towards large particles, which I'll explain a little bit about in a second. But knowing that it's always biased towards large particles, it essentially means if you say, for example, in this example, had some nanoparticles that were 50 nanometers in diameter and some that are 5, your 50 are going to completely overcrowd your 5. So it looks like you've got a larger proportion of those 50 nanometer particles. And what the DLS can also do is apply, again, some more algorithms and clever maths, and using something called my theory to convert this intensity plot to a volume plot and then a number plot, and which will essentially reveal a bit more to you about the proportion of your different size particles. So in this kind of really clear example here, whereas here it looks as though you've got lots of 50 and little of 5, when you convert it to a number plot, you actually see that you've got them in equal proportion. And it is this, the mass that's applied to this number plot is what's going to actually more accurately reflect what you see as the size from other types of techniques, such as TEM. So if, as much as it's not recommended to compare sizes from different techniques, if you were ever wanted to compare DLS size to a number size, then to TEM or anything like that, it's best to look at the number plot.
I was just going to say that this is like the key weakness of DLS, basically, isn't it? Because when you've got heterogeneous particles, because if you double, let's try and work this out. Yeah, I can't quite remember. So it increases the amount of light that you reflects from a particle, increases to the power of 6 relative to the increase in the size of the particles.
Yeah.
So that's basically what that one on the left shows, isn't it? So if you've got equal numbers of big stuff and small stuff, you might not even be able to resolve the small stuff because the peaks is so much smaller that your deconvolution software would never even know it was there because it's so insignificant. It's like noise almost.
Yeah.
So I think this is the key reason why people suggest that DLS is used for samples which you know about, so you know what you should have, rather than heterogeneous samples where you don't really know what you start with.
Yeah, absolutely. Just remembered one point that I also perhaps should have emphasised, just going back a little bit, that your what's really important to note when you get your Z average or your hydrodynamic diameter, it's important to remember that the that size it's giving you is the size of a particle that is a hard sphere and is travelling at the same speed as the particle you've measured. So it's not the actual diameter of your particle, it's the diameter of a hard sphere particle travelling at the same speed. If that, yeah, just really important to distinguish that. So that's why we refer to it as the hydrodynamic diameter rather than it actually being its physical diameter. Okay. So there's a few variables which can influence a DLS measurement that I've recently also learned about, which also can help you interpret your data a bit more thoroughly. So can work through these, but at this point, is there any questions or any comments? Anything people didn't quite understand? Nope. Okay. Cool. So the first thing that influences a DLS measurement is an angular dependence. And when I said earlier that it has this bias towards larger particles, this essentially is the theory behind that. So when a particle has a diameter that's less than 1/10 of your laser wavelength, when the laser, which is this red line, hits that particle, the scattering is going to spread out isotropically, so evenly in all directions. And that's worked out by something called the Rayleigh theory. But when your particles are then greater than 1/10 of the laser wavelength or equal to or much larger, then what's known is when light hits that particle, the scattering will always be slightly distorted in a forward direction. So you can see in this little diagram here that you've got some particles which are 1,000 down to 500, and the larger particles are really going to heavily scatter in this forward direction and shadow any smaller particles. And it's my theory that essentially explains this, which then is why in a DLS machine you have certain detection angles. And I found this diagram to be quite helpful. That and a question that was posed in one of these webinars I was listening to was, if you had some small particles and large particles, which detection angle is going to be better to use? And the answer to this being, it's going to be better to detect your sample at a backscatter of 173, because when you have your laser coming in, the area that you're going to be measuring is going to be much larger than something off to the sides. And so in this larger area, you can detect more of your big and small particles. And also, if you look at this my theory diagram, you can see that you're removing a lot of this forward scatter influence, and yeah, you have a large area with which to see these multiple different size particles. But if you can still see, even at this 173 backscatter, your larger particles are still going to take up more of that scattering. You're still going to have that bias, but we try and remove that as much as possible by measuring from this 173-degree angle.
Can I just ask, the wavelength that the machine uses is about 700 or 800, is it? Is that right?
I can't remember off the top of my head, but yeah.
It's red light, isn't it?
Yeah. Yes.
Oh, I don't know. Can't remember. I was just trying to work out what a tenth of it might be, and if it's 800 or 700, it's like, what, 70 nanometers? But I don't know.
Yeah, I can't remember. So yeah, that's basically the angular dependence of your machine, and why you in the old machines your reading always comes from this 173-degree angle. So the second thing that can influence it is your measurement position, and that's explained a little bit better here. So in a DLS is quite clever in that it will automatically find a measurement position, and it does that depending on how concentrated your sample is. So a measurement position will either be at the centre of your cuvette, or it can move towards the edge of the cuvette. And you can see perhaps in this diagram down here that if you were to have a really concentrated sample, something in if you were to move the measurement towards the edge of your cuvette, it's going to be as if it was a lower concentration, and therefore get a more clearer reading. So the most ideal position obviously is in the middle, where you have little laser flare, because if up here, if your sample was completely clear and you were measuring at the edge of your cuvette, you would get a lot of laser flare, which is this jaggedy signal you see here. But if your sample was completely over concentrated, in your corellogram, you would find that your intercept is quite low. Sorry, this is quite blurry here, but it's below 0.8, which is why the machine would then perhaps move towards the edge, which is this plot here, and then it improves that signal to noise ratio and gives you a much better realistic reading. So two things to be taken from this. If you actually then look in your raw data at your measurement position, if you find the machine has had to move to the edge, it can inform you that perhaps your sample needs diluting to have a better reading. And ideally, you would perform a serial dilution of your sample and check that the size is always consistent, so you'll know you're then working in an optimal concentration range to get accurate size readings. Does that make sense?
Yeah, I guess that's kind of, the machine probably sort of does that sort of thing for you, and that's when it says the sample's crap or something.
Well, it was still, if it finds it can have a good reading at the edge, it will still pump it will still say that's good. So I suppose it's always worth noting where the machine had to find a good position, and if it is more towards the edge of your cuvette, then it shows you that perhaps you could do with diluting your sample.
Yeah.
Can I just ask a quick question? Oh, sorry.
Yeah, go.
I was just going to say, what is to the edge? Like, is a lower number to the edge? Sorry.
It would say.
Yeah, okay, fine. So, fine, yeah. So 4.56 is in the middle, sort of thing. Okay.
Yeah. 4.56 middle, and towards the edge is like 0.85 going. Yeah,
that makes sense. Cool. Yeah.
I guess as well, there's also, if you've got a turbid sample, you've got more, scattering and reabsorption and then rescattering and things like that, which make it a much less accurate measurement.
Yeah.
Right, because you just let a lot of the light's lost.
Yes.
I think that the whole, I would, if I were trying to using the machine for the first time, I'd be testing dilutions anyway, just to sort of check that the machine knows what it's talking about.
Yeah.
Do you know what I mean?
Yes. Yeah. It is recommended to dilute some samples and you're getting consistent measurement.
Especially when the samples you don't really know too much about it. If you haven't made it in a rigorous way, like for instance with liposomes, you push them through a filter, so you know pretty much that they should all be 100 nanometers. But if you're using sonication or something, you've got much less control. So therefore, you need to be you need to be much more prudent with how you take your measurements and how you interpret your data.
And the other thing that is involved in this measurement position is the attenuator. So your attenuator essentially is going to control the intensity of which the laser is put upon your sample. And again, the machine will automatically assign this. So if, for example, you had a really concentrated sample, then it's going to set its attenuator to a really low level to block out a lot of that light. So you don't get so much scattering effect from your really concentrated sample. Whereas if you've got a really dilute sample, then it's going to be wanting to project much more light onto that to try and get a better signal. So again, if you are looking at your raw results and you see that the attenuator position was a kind of middle number between 1 and 11, then that shows that that it wasn't too concentrated and it wasn't too dilute. You've probably got a good level reading there. And if you were comparing two samples and you found that your measurement position or your attenuator setting was changing, then it can inform you between those two samples which perhaps is more concentrated than the other. And then the final thing that the machine also is a variable that it can set is the duration used to take your measurement. So that's something manually you can set yourself, or you can allow the machine to do it automatically. And essentially, because the raw information that's coming in is just photons, counting photons, it will change the duration if perhaps your photon count is too low, or if it's too high, it's going to measure it for less time, basically. And so it's important to bear in mind that the duration of measurement is always determined from the count rate. So the lower the count rate, the longer the time, and that usually it does this by having those subruns. And so it takes lots of subruns and then looks at the count rate for each of those subruns. And the default software is any subruns that have a really high count rate, it will remove, because it expects that this high count rate, i.e. meaning there was perhaps a big spike in the number of photons from perhaps a bit of dust coming across your sample and then moving away again, it will remove those from your interpretation. So only 50% of the data that it collects, those with the lowest mean count rates, is used in your cumulants and distribution analysis. And one thing to note here, perhaps I'll bring in here, is I've read that the DLS Ultra, our new machine, actually doesn't do this. rather than just getting rid of the data, it stores it. So you can go back and look at that data and see if your sample had a lot of kind of dust interfering with it. Yeah, but old machines would just remove it. Yeah, so that kind of overall is all the information you get given, and then finally it will give this results quality as to whether it's good or bad, and depending on what your other values are, you can then go through a process of elimination as to what you could do with your sample to improve it. And obviously the one final thing that they always recommend to do is to do some technical repeats, and that can actually give you, again, some quite useful information about your sample. If between your technical repeats you're getting the same count rates and the same Z average, or at least within a few % of one another, then you've got a good sample. If you find that your count rate or your Z average is increasing, that suggests that your particles are probably aggregating over the time that you're doing these repeats, or that your temperature is not stable. Versus if this count rate was decreasing or your Z average was decreasing, that can suggest that your particles are sedimenting or dissolving. And if there's quite a random fluctuation in change, then it suggests they're not very stable. If you find that your peak position, your peak readout from your distribution analysis is changing, then that suggests you might need to be taking some longer measurement time. So that's just, again, it's a bit of information you can get from doing your technical repeats. And then I've kind of got a few slides here where it just goes through problems and what the solutions could be, and I can send you guys these slides if that's helpful, or it's all on the Malvern website as well. That, yeah, if you've got your PDI is perhaps bigger than 1, then that suggests you've got dust particles, or it could be that you the machine itself is not set to automatically find the position in the QDEC. So you just check that the settings are automatic, and it will help improve that reading. And then there's a number of things. We mentioned earlier about the intercept on the y-axis, and why if you ever find that it's over 1, that suggests that you've got a really noisy baseline. So i.e. there's either sedimenting particles or clumps of dust, and that's had to shift your intercept much higher. So the solution to that is filter your sample or dilute your sample. Again, we said about looking at your count rate and looking at the number of photons collected, and whether check that things like your attenuator and your position is automatic. Sometimes if your sample is has a colour and absorbs light, this can affect the count rate, and that's where you might need to be using a different laser wavelength, which will depend on the machine. Old machines, we can't do that, which is why we often try and avoid putting in really coloured samples. And then a final other bit of information that you can look up in your report is you can see how well the plotted exponential decay from your cumulants analysis and the plotted exponential decay for your distribution analysis fit to your raw results. So you can look at your cumulants and distribution fit error, and you're looking for something that's quite low. If you've got quite a high fit error, then it would either mean that you need to, as I said earlier, if it doesn't fit on your cumulants analysis, then just pay attention to your Z average from your distribution analysis, or it could mean you need to filter or get rid of any large particles. Yeah, and then finally, just a few little things of how the Zetasizer just makes this all so much better. This is a bit that I hadn't really fully finished, sorry guys, is that you can look up that data I said that it gets rid of, so you can really see if there's some large particles interfering with your reading. You can go back and check that data and information, and it takes these subruns much more quickly to allow for this what's called adaptive correlation. And then finally, also the best thing about the new machine we've got is the fact that it, rather than just looking at backscatter, we can look at forward scatter and side scatter, which will give a higher resolution of what particles are present, and also can be used to, when you take into account you subtract the scatter that's the result of your dilutant, again with some clever maths, you get the concentration of your particle. Yeah, so that's a very quick overview of that last bit. But any questions?
That was really excellent, Leafy. I'm really glad I recorded that. It's a really nice overview of it all and really useful slides. It's a good place for people to start who are just using DLS. So really appreciate you doing that today. Has anyone got any?
I was just going to say, I did find that it was useful for me to go, even though I didn't know a lot of this up till recently, things like the corellogram, I was able to go back and pull that information from my data, and thankfully they all looked nice, but it was just something that could bulk up understanding the data I got, and I can talk about it a bit more in my thesis and that sort of thing. Yeah.
The polymersomes have always looked pretty monodispersed.
Yeah.
Which is pretty amazing considering, you know, they're not made in you just drop stuff. Yeah. So it's the power of chemistry, isn't it?
Very much so.
Thanks, John. So, has anyone got any other questions?
I can tell you that the wavelength of the laser is 633 nanometers.
Yeah.
Cool. Thanks.
I'm sure you are all dying to know that.